There you go. You are a wiener. We're all wieners. Oscar Mayer wieners, to be precise. Okay, I can't sing that because all I know is really dirty words. Visual display of data. So we've been making plots already. Prior to that, for the last 3 weeks, we just gave you a script. It says use the plot a bear script or use the plot 2 lines, and you just put in the series. Now we'll get a little bit further discussion on what was going on under the hood. Today's overall objectives are to list some common plot types and their uses. Actually, we're going to get to identifying the parts of a plot, and we'll get to see what these fancy words, ordinate and abscissa, are. These are big uppity words for left, right, and up, down axes. I personally find left, right axes and up, down axes far easier to communicate to each other with. It doesn't sound very intelligent or professional, and that's probably why. Never mind. And how to plot the difference between experimental observations and model results. I'll get to those as we get to them. Our main tool is our friend Matplotlib, and it's a collection of plotting functions that kind of work like MATLAB, and I suspect it's funded by MATLAB, so it wouldn't be stolen from them. And the general way we're making graphics in our Python scripts is we're actually building up features of a figure, and when it's done, we go ahead and we show it. So sometimes that doesn't work, and you get the blue screen, the pink rectangle of, oops, I made a mistake somewhere, and you have to correct it. The main library we're using is Pyplot, which I assume means Python plot. And there's a couple ways to, fancy word, invoke it, a couple ways to load it in to make it work. We'll get to that shortly. Somebody just got a text message, so go ahead and secretly take that, because you know you're not supposed to get text messages in class. Yeah, if you had one of these piece of shit apples, it can go straight to the computer, and then it doesn't make the ding sound. Yeah, you're going to have to trust them. There's no other way. Yeah. Okay, so let's look at some graphics conventions for plots. So these, the word convention means a collective agreement. So we collectively, I want to see what it is now. You have been signed out.
He really doesn't like it.
Yeah, it's one of those. I think it's still recording. Yeah, your young eyes are seeing the little recording symbol still going. And that was a compliment, so don't take that as offensive. People, blur. Able to operate a motor vehicle, hazard to navigation. I would imagine everybody in here who wears glasses has that same feature. You know, if we ever collectively decide that we can't stand society anymore, we take the glasses off, get in our car. Massive 2000 car wreck in Lubbock, Texas. To motor vehicle operators who took their glasses off. Yeah, at rush minute. Okay, so let's continue. That was all my tangent, none of your fault. So we're going to introduce 2 terms, ordinate and abscissa. Use those when you're trying to convince people to part with their money, but all it means is up, down, and left, right. So by convention, the abscissa is the left-right axis or the horizontal axis on a plot. And the ordinate, by convention, is the vertical axis, also known as the up-down axis. So everybody in this room can handle left, right, and up, down. I don't care if you don't know which your left and your right is, as long as you know left, right is this way and up, down is that way.
Or just like Directional.
What would be up, down, left, right dyslexia? I mean, that'd be seriously dyslexia. That would be dysgraphic, which is a real thing, by the way. Dysgraphia means you can't draw pictures for crap. It's the same thing that you experience when your brain seizes up and you start flopping around like a fish. Okay, so a few terms in describing data models. There are independent variables and dependent variables. So independent variables are the variables that file the federal income taxes, and the dependent variables are the variables that the independent variables claim. Just kidding. The independent variables are variables that we generally accept that we have some sort of control or manipulation capability. So an example would be the famous equation that everyone's comfortable with, F equals ma. So force equals mass times acceleration. Now let's think in our heads, which of those variables do we have some control over? I'm going to use mass as my independent variable, so I can control the mass. I'll assume I have uniform acceleration, and if I double the mass at a constant acceleration, I'm going to double the force. If I half the mass, I half the force. How do you half the mass? Easy, cut the leg off, and all of a sudden your body weighs less than it did before, so there's less force on it. There's also less blood in you because it's going to be squirting all over the place and making independent variables, mass. Dependent variable in that mental model is the force itself. So if we double the value of the independent variable using that particular model, then the dependent variable doubles, the force goes up. Now, there's not necessarily a one-to-one relationship, but there just was for that mental model. Okay, so that was a pretty grisly mental model, appropriate for the French Revolution, because during the French Revolution, the regular people decided the aristocracy had too much mass. And basically, they all had one head too much mass. And so by removing the heads, they brought them back down to the level of the regular people. Yeah, and it.
Because they use space rather than time.
Yeah, I think so. So the plotting convention in most cases assigns the explanatory or the predictor or the feature or the independent variables to the left-right axis. Not always, but most of the time. And then the response variable or the prediction variable or the dependent variable is assigned to the up-down axis. Again, most of the time, not always. So if you were presented with a quiz like we used to do in the old days, so here's a quiz question for you. The abscissa is A, the horizontal axis, or B, the vertical axis?
A.
A. So we have one vote for A. Would you like to consult the rest of the audience? What do y'all think? You're right. It is A, the horizontal axis. It's you're still not sure? Okay, so if instead we said that the left-right axis, that would be just as correct. Okay, so conventions for plots, and proper is not the right word, but whenever I was typing this, that was the first word that came to mind. We always want to include a title or a caption. So if we go back to this plot, ooh, that's a bad plot. No title, no caption. So fail that plotter and I have to go take the class all over again. You don't want to be in that situation. I can't imagine having to sit through me twice. So we want to get in the habit of including a title or a caption in any plot that we make. And those generally got to be somewhat meaningful. So putting the character string title in, while technically correct, is not a particularly descriptive character string to describe a plot. So if the plot is named title, you don't know what it's a plot of. What's the difference between a title and a caption? Anybody, those words mean anything to you? Titles are at the top, captions are usually, let's see if I have an example of a caption. I don't think I have any in this one. When you see my notes and it says figure 17, plot of cats versus dogs, that's a caption. Captions are by far the more common. Let me get back to the title, because I'm now starting to act like a TA and flip up and down so nobody can pay attention. Sorry about that. That was mean of me. We also need to label the axes. Again, meaningful labels. X-axis and Y-axis, while technically correct according to these rules, aren't particularly useful. So what we want in the axes label is usually what's being plotted, the variable name, possibly the symbol for the variable, and definitely the units for it. So for instance, if we're plotting time and density on the same plot, we'd certainly write the words time and density, probably include the symbol for time, which in this particular case is T, and density, which is rho, and then the units, in this case seconds, and this grams per milliliter.
How would you input Greek letters in case of some scientific plotting?
You'd have to know, there is a way to do it. I'm trying not to be a smart ass. You'd have to put the latex equivalent of, we can try that in a little bit. I can show you, for instance, wrong. Let me show you one where there is a lot of Greek letters. There we go. Fluid mechanics. So this is not this class. But it's interesting that you asked that. I think I have one with a Greek letter in here somewhere. I'll just show you what the typesetting looks like if I can actually find it. There should be a row V here. There it is. So there is the, these are latex commands. So that is the markup system that's used in Jupyter books, latex. And so \RHO is the row. And then these other decorations, you'll have to look them up on the internet. And I've actually never tried it in a Python plot, but it should work. Or it should give you the pink block of error. So the other way to do it is to save the Greek letter as a graphic. And you can plot the graphic in the title. That is a very advanced technique. High probability of error. Well, it had, the subsystem has to know that \RHO is a latex command, and it has to have the latex subsystem installed in the kernel. So we can try that, but the point of your question that's important is, yes, it can be done. I don't necessarily know how to do it right now. There's always the old-fashioned way, which is print it out and use. But nowadays in computer land, that's just so uncool. All right, so, and the question is a legitimate one, given that I have the symbol rho right there. Okay, so user descriptor, title, or caption. I think I beat that horse to death. And because we have a choice of the numerical increments that are plotted, the best advice is scale increments that are easy to read and interpolate between and kind of make sense. So typically things like 1, 2, 2.5, 5, 1 through 10, 0, 20, 40, 60 is typical. The values, those particular ones can be scaled by any power of 10 quite easily. Unless there's a really good reason to, don't use weird increments like 3, 7, 15, or 3, 7, 6.5, 15, 22. And a really good reason is not, those are the only increments I could get the picture to plot in. I mean, although I understand the sentiment there and probably have thought it myself on more than one occasion, that's not a good reason to use those increments. Because if that's the only way you can get it to plot, you've broken something else much worse. Include grid lines, and I don't actually know the command for that. Show the experimental measurements as symbols, so that is important. And theoretical values are shown as lines. Okay, so now we're going to put up a plot, and I'm going to point to some things to it. Because first I'm going to point out to a major oxymoron. Everyone know what an oxymoron is? Do not point to yourself.
That's what makes it not so warm.
Fair enough. So it says theoretical data. There is no such thing as theoretical data. If it's data, it's data. It was measured. If it's theoretical, that means it's been pulled out of somebody's datum. A datum is what you're all sitting on right now. So that probably should have said data model or model data or something like, or model results. So observations, things that are measured by convention are plotted as markers. There's no line joining. We sometimes have to tell the computer program to not join things with lines because the people that wrote the computer program figured the business school was going to use it. Business school likes lots of trend lines. Well, here's how much money we're making today. Here's how much money we'll make tomorrow if I can get you out in the parking lot and roll you and take your wallet. Okay. If we have a model response, so our F equals MA, F equals MA doesn't really care where you are. If you're on that line, it is predictable. And so that's the key message I want you to get here between the red dots and the blue line. Things that are observed or measured or go by the name data, not the character in next generation, but data, are plotted as markers, always. There is almost no exception to that I can think of. The only possible exception is I forgot to turn the lines off, and I needed to get this out because the client expected it yesterday, and it turned out the money was going to evaporate. That might be a very weak justification for doing that. And then model results or calculated results are plotted as curves, always. Let's see here, it says make portrait orientation when using your plot. I don't even know if that's a thing that we have to worry about. Make the plot big enough to be easily read. So that applies to all of you. I'm not calling anyone out now because I actually haven't observed this, but back in the olden days when I first started teaching college, that was like 35 some odd years ago, people would hand in pictures like these teeny things. They write microscopic. It was legible with a magnifying glass. That's just rude. Okay, if you're going to do that, don't even put the plot in at all. Make it big enough for your audience to see, because we're making these plots really for one reason only, and that's to communicate information to an audience. And generally, the audience is probably someone at the vice president level or higher who, through the process of getting elevated to that at their company, has an IQ that's reverted to that of a 4-year-old. Adult body, huge paycheck, 4-year-old intellect. That's what you're dealing with plots. So we got to make these things big and colorful.
That sounds like John. Yeah.
I'm glad you all grinned at that. Thank you very much. Big and colorful. Distinguish if you have multiple series being plotted. So maybe you're plotting 2 sets of observations because you want to show that salt water tastes different than tap water. Then in that case, not only do we want to use different colors, we also want to use different symbols. There's actually a very practical reason for doing that. What happens when these plots get printed out? Let's say these are plots for a doctor's office. Anyone ever, you guys are all young, you maybe don't go to doctors. Some of you do. What do they do when you go to a doctor's office and they give you the instructions on how you're supposed to treat yourself? It's a photocopy of a photocopy of a photocopy. And you're looking at this thing that they hand to you, and it's like, son of a bitch, I'm paying $135 copay, and you're going to bill the insurance company $3,000, and the best you can do is a photocopy of a photocopy of a photocopy. By the way, don't have that conversation. They don't want to hear it.
I'll have that conversation.
I'll make sure to bring that up.
But if you're militant enough, you'll actually get the original thing in the nice plastic laminate. And that the argument I just described is the one to have, having done that myself. My regular doctor doesn't do photocopies of photos. You can see him, he'll tell the nurses, yeah, don't give him the photocopy shit. Go get stuff from the real room. So why? He gets really pissy about it. Anyway, that's why you use different shape markers, because if it does get photocopied, photocopiers lose the ability to maintain color. You can't make color photocopies. They used to be ungodly expensive. I think now they're just expensive. So it used to be a black and white image was 2.5 to 5 cents an image. And at the time, color was $1 to $1.25. I don't know what the differential is now. Okay, so it's pretty close now. But that's why we use markers, because if you lose the color, you can still interpret the results if you can tell that a triangle is different than a circle is different than a square. Avoid light colors or yellow, especially if you have a white background. If you're the TA who is enamored with dark backgrounds, yellow and light blue will show up real pretty. But for the rest of the world, which works with white paper backgrounds and then you put content onto it, avoid colors that can't be seen. And this actually probably applies in making a presentation. You don't necessarily know what the background shading is going to be. So you want to use something that will work well in either a white background or a dark background. So a black printing won't work too good in dark background, but most computer programs have been taught, if you're doing a dark background, assume that the font needs to be converted to a light color, either white or light something. Include a legend if 2 or more data sets are to be presented. You don't need a legend for a single data set because apparently single data sets are not legendary, but 2 or more are legendary. And the legend is just an indication to the reader of which markers and which colors correspond to what particular series. So here's an example of a correctly drawn plot showing experimental data. It has one flaw still. Who can identify the flaw? What's missing? It has no title. I guess you could argue technically figure 11.5 is the caption, but I think this one would be flawed. -5. Get to take the class all over again. In this case, we're plotting something versus something. What's the variable? It is the independent variable, the predictor variable, the feature variable. It starts with a consonant. The predictor is conventionally plotted on the, is that because it marks the spot? Good, good. It's on the left-right axis. So which variable is on the left-right axis right here? So you don't even know what's being plotted. You can immediately look at that graph and know that the height is what's being varied. And the symbol they're using for height in this case is capital H. And the units of height is meters. Very good. And given the magnitude of those values, they're probably talking about how high up to put a swirly thing to make electricity. And I know that because the other thing being plotted is power. And there are very few 120 meter tall basketball players. So although I imagine height and power are directly proportional in that field of endeavor also, since the power is plotted here, that's what I think. And this also brings a very important point. This is a classic case of mixing SI units on the left, right, and US customary on the up, down, because everyone knows that horsepower is somehow correlated to meters.
Shouldn't that be joules?
Yes, it should.
Or at least megajoules if you're talking about.
Horsepower is energy per times. That would be watts. which is joules per second, a certain amount of joules per second. Anyway, horsepower is not the correct SI unit, because there are no horses in the rest of the world, I guess. Continuing on with that, in this case, we have two data series. One is for things that have a mass of 100 kilos, and the other one is for a mass of 250 kilos. And based on this plot, so here we'll again illustrate how rapidly you can communicate stuff with pictures. If you had to decide how to get more power, do you make things heavier or lighter? Tell me how you came about that conclusion. I can outlast you all. There's only 20 minutes to go.
Usually you'd make it lighter.
Okay, but is there any evidence in this graph to support that conjecture?
No, because
Yes. The 100 gram series lies quite a bit above the 250 kilogram series and powers in the up-down axis.
sorry, I'm looking at you.
Look at the plot. It's much more interesting.
I gotta read your roots.
Fair enough. So let's see, is there anything else to describe about this plot? No. This is the legend. It's legendary. And now we'll look at another one, which is not experimental data. This is I take offense at the words theoretical data being next to each other. That makes no sense. Example of a correctly drawn plot showing a data model. That I could live with. A theoretical data model, a theoretical relationship, something like that. But you don't have to that as much. Here we're plotting only one thing, so there's no need for a legend. So this is not very legendary. On the left-right axis, what are we plotting? Good. On the up-down axis? Yeah. And then it gives the units. And we have scales as appropriate. The spacing is about right. And the key thing here is we're not wasting real estate, although I guess you can argue we are. But the line is using up a whole lot of the plot on purpose. It's supposed to. A piss poor plot would be to take that same line, readjust these scales, so there's only a little teeny line segment right here. That would be a monumental waste of real estate. We know that this is a data model, not only because the caption tells us, but because the plot is a teaching 101, look around the class, patiently waiting for somebody to blurt out an answer. If it's even remotely correct, say yes, and then move on. Oh, you guys are going to outlast me. We know it is a data model because the plot is a line. Excellent. Well, they're easier to answer if you understand them. I'll grant you that. But the best answer is just blurt something out because it makes the class go faster. Even if the professor jumps all over you and calls you an absolute moron, it'll get by faster. They shouldn't do that because that's just insulting. So let's look at line charts using Matplot library. So line chart or line plot or line graph or curve chart or something like that is a type of chart which displays information. If I ended the sentence right there, that would be a classic talking in your sleep. As a series of data points called markers connected by straight line segments. That's the key thing. Line charts use data points that you provide to the plotting tool. It makes markers and it joins them with straight lines. It's a basic type of chart common in many fields, in particular business. It's similar to a scatter plot, except the measurement points are by convention ordered. They're expected to be in some kind of order. We'll see an example shortly of what happens when we violate that expectation. Dude, you got to give me 10 more minutes. You're packing up too quick. A line chart's often used to visualize a trend in data over intervals in time. If that's the case, they're called time series, and thus the line is often drawn chronologically. The x-axis spacing can sometimes be tricky. Hence, line charts can unintentionally deceive. So you can deceive yourself without intending to. More importantly, in the hands of a skilled chart maker, line charts can be used to intentionally deceive. So be sure it's appropriate for your data and don't try to intentionally deceive people because you're not working for the federal government yet. As an example, let's consider some experimental data below. Suppose we had some way of measuring time and speed, and we have this series of the first 6 seconds of the existence of something. At time 0, everything's setting put. A second later, it's moving 3 meters a second. Another second, 7 meters per second. 6 seconds from the beginning, 45 meters per second. Are there things on this planet that accelerate that fast? Elizabeth, you can answer that one because you're wearing the NASA logoed stuff. You're not even here today, are you? I said, are there things on this planet that accelerate that fast? That'd be a yes. They accelerate even, they accelerate even faster. Yeah, there are things that accelerate that fast. You should be thankful you don't have the morning lab when he's first starting his first gallon of coffee. You've had it after he's only had 6 gallons of coffee. Yeah. So let's suppose we wanted to show the relationship between those two series. And we might want to do that to ask the question, is the relationship indicating acceleration? That'd be a yes. So let's go ahead and make a plot. So to do that, we would import our package. And this is one of several ways of importing the package. So from Matplot library, import pyplot as PLT. When that's done, what does PLT represent? First person says truth, justice, and the American ways, and you get something thrown at it. So what does it represent? Pyplot.
Oh,
You're right. You're close. You're very close. It represents the pyplot function.
you said PLT.
Yeah, I said, what does PLT represent? Pyplot, which is part of Matplot library. Good. So another way we could have imported that is the way I would do it, because I like to type a lot, not really, but I do use the miracle of cut and paste, which would be import matplotlib.pyplot, be normally how I do it. Different ways to accomplish the same things. PLT for this case makes a lot of sense. Now we'll create the two lists, time and speed. So here's time right here. And where is time?
Relative.
Oh, I was hoping you were going to say it's on your side. Time is on my side. Mick Jagger, 1962. Well, no, that's oldies music that you're going to hear in the nursing home when you come visit me. And then speed is shown here. So those are those two columns right up here, just entered as lists. Okay, so nothing surprising there. And now we'll create a line chart. So to do that, we will create an object called my data, because that seems like a good name. Anything. We'll invoke the plot function. We're going to use the figure command, and all we're going to do is set the size of the figure. So this is the equivalent of that landscape portrait thing that was discussed earlier in how to make plots. So the 10 by 5 means it's going to be 10 units wide, 5 units tall. Now, I don't actually know if it's inches or parsecs or something like that. It's too small for parsecs, but also seems too small for inches. You can adjust these numbers to go ahead and get the drawing size the way you want. And I have an incorrect statement here. It's a rectangle, not a square. And then we will invoke the plot command and choose plot, which makes a line plot. We're going to tell it to plot time on the left-right axis, speed on the up-down axis. C equals red, we're going to make it in red. Marker equals V, which is an upside down triangle. And line width equals 1, which sets out the line width. And finally, when we think it's going to work, we tell it to show the plot. So plot.show is what renders the plot. And there we go. We got this beautiful plot, red line, starting at 0, 0 and working its way up. Any flaws in that plot based on our plotting convention? No, it's the opposite of no, it's yes. Axes aren't labeled, there's no title, there's no caption. But as
Yeah, I know, right?
and that is why you guys will go nowhere unless you start labeling your axes and so forth. Now let me show you what happens if we take the same data, the same relationship. So the times are all paired with their appropriate speed, except we move times 4 and 5 somewhere into the middle of the list and their commensurate speeds, and then plot that in a line plot. We get this green abomination. So the markers are in the correct place, but the lines don't seem to make sense. What's going on there?
We're down one flight group.
Possibly. So line plots by design are expected to be ordered. So this was our first data pair. This is our second. That one happens to be our third, fourth, fifth, sixth, seventh. Now, if that was not the intent, we get that abomination there, which is very confusing. And if you assume it's right, you hand it to your client. The client goes into the room, it's way out here and says, we hired a bunch of idiots. Let's get rid of them. Write them a check, get them the hell out of my office. That's okay for that check, but you don't get future checks. So if that was not the intent, this is the wrong kind of plot. If all I want to do is plot markers that we know are paired with each other, we want to choose a scatter plot. And we'll get to that next class meeting. So I still own you for 3 minutes. Actually, I never own you. Let's suppose that we want to use the plot to do something useful. So we're going to do an Evian acceleration estimate. Evian, as you know, is probably what's in this blue water bottle. Evian is naive spelled backwards. That's how I remember how to spell naive. So thank you to the Pepsi-Cola owns them. Or whoever owns them, thank you to whoever they are. Because of them, I could spell naive every time. I just think of the bottle and the pink bits. And if we wanted to naively estimate acceleration, a reasonable guess would be to take the maximum speed, subtract from it the minimum speed, divide that by the maximum time from the minimum time, which is the change in velocity, divided by change in time, which by definition is dv dt is equal to, come on, you had it in P physics. Change in velocity over change in time has another name. Yes, thank you very much. And you can know that because the word is right there. It's just yelling at you. And so now we make the two plots. So here we have one called data, which is the red triangles, and we have our blue acceleration line. And from that we can conclude, well, the average acceleration suggested by this collection of observations is 7 meters per second. And we know it's an average for a couple reasons, because it says so. More importantly, at the beginning of the launch of this thing, the acceleration is less than the average value. How do we know that? Because the slope is less than the blue slope. And near the end of it, the slope is quite a bit steeper than the blue slope. So we're averaging over that. And maybe the average is good enough for something we want to do with this data. We can also make charts in Pandas. And I believe you did this in the last lab. In fact, I know this is the same database. So here's the census one. The charts appear to be slightly easier to construct syntactically, but it's really the same thing. You have to tell it what's going to be on the left-right axis, what's going to be on the up-down axis, whether you're going to label it, what color you want it to be, and whether or not you want to label the axis values themselves. And to make multiple plots on the same thing, just like in Matplot library, where here you notice we plot one thing, and then we plot the next thing on the plot, and finally we show the plot. We're doing the same in Pandas using the axe feature. And so there we get multiple plots. And that is all for today. Before you run off, let's go take a look at the laboratory you're about to be inflicted upon. What about it? It should be up there because I just helped somebody work on it a few hours ago. Oh, Jesus, that's right. There's two sections. Thank you for telling me. While you guys are enduring lab 14, I'll get all that stuff linked in so you can hand it in late. I'll fix the dates. Don't sweat it. What was it? Oh, so here's your lab 14. So here's what Josh is supposed to go through with you. A couple of columns of numbers, pretty much identical, different numbers, different process. And you're given the plotting function ahead of time. And then you're going to look at a couple of different data models, a linear data model, a quadratic data model, a power law data model, and residue, which is a residual, which is the difference between your observation and your model value. The residuals get small, and you add them all up, we go, oh, that's cool, a model is awesome. If the residuals are huge, that means the model is nowhere near the observation. So if we go back to our previous deal, let's go up here. So the blue line is our model. Let's just pretend that. So is that a very good model of these data or a very bad model? Can you think of a better one? I guess that's how you should ask the question to yourself. Do you think you can do better than that blue line? That'd be a yes. I could shift the blue line down a little bit and probably get it to pass through 2 or 3 of the markers instead of just hitting each end. The metric or the measurement we use for that is what's called the residual, or I call them residues. And then you have a homework assignment, which is different set of data. This is where you get to go design a proper therapeutic drug threshold. So you got to decide if the linear model or the quadratic or a cubic or a power law model is the best way to dose yourself. And then once you've picked your favorite model, then go ahead and dose yourself with this particular drug. I'm not trying to encourage you to become drug addicts. More importantly, this is actual somewhat real data from a real paper from 2007 when you guys were just a mere 19 years old, just practically yesterday for you. So that's all these lab and exercises are for today. I will set you up for lab in about 10 minutes. And 11 minutes now, 12.
So I was looking at this blackboard right here, and it's saying I got a 0 on this, and I didn't even do this.
Oh, don't sweat that. Did you get a non-zero somewhere else?
Yes, sir. I got it on one of I got like a 40.5.
Don't worry about it.
Okay, awesome. Thank you.
There's like 6 different tests because a lot of people had different problems along the way.
Okay, thank
So what's up with the welding thing?
I haven't followed up on that, sorry. I figure you got plenty of other stuff to entertain yourself with.
Yeah, I'm dying writing a business plan right now.
For your robots?
I'm starting a company.
You are, what are you gonna sell?
Robots. Yeah.
Cool.
Um,
Are you serious?
fully
Yeah, like
autonomous
how?
robots. I gathered a small team. So,
Cool. What are these robots gonna do?
yeah, well, the one of them is gonna be fully autonomous. It's okay, so tech has, the innovation hub. So they have a social innovation